Hey guys, uh, here we go. This is a short video that is going to review the stoichiometry that we had learned thus far before the schools had shut down. So this is just an opportunity for you if you just want to get a quick refresher on what we did so you don't forget. At the end of the video, I will provide some resources for you to practice as well. So first of all, welcome to my house. This is what we're going to do. The moles made it. They're safe. They're here quarantined with me. So they're going to help me out here a little bit. All right, here we go. So, stoichiometry, the math of chemistry, basically the art of conversions. I had taught you a handful of conversions before we had left. The first one being Avogadro's number. Avogadro's number. So 1 mole is equal to 6.02 times 10 to the 23rd. And that can be of anything, particles, compounds, molecules, what have you. Basically, it's just a word, mole, that represents a number, 6.02 times 10 to the 23rd. The idea is atoms are so small, having such a large number of them, like 6.02 times 10 to the 23rd, actually is practical and makes sense. So rather than saying that huge gross number all the time, we just say mole instead. The other thing that we had learned was molar mass. So 1 mole of a compound is equal to however many grams. These molar mass values can actually be found on the periodic table. So for example, 1 mole of oxygen is equal to 16.00 grams. 1 mole of sulfur is equal to 32.06 grams. So these average atomic mass values are also how many grams 1 mole of that atom weighs. And remember, when I say mole, I mean 6.02 times 10 to the 23rd. The other thing we learned was molar volume. So gases are unique and they all behave the same way, regardless of the identity of the gas, the molar mass of the gas. Once a substance is a gas, they all behave the same. We're going to dive into this more later, but what this means for you right now is that 1 mole of any gas is equal to 22.4 liters at STP. Remember, STP stands for standard temperature and pressure. Standard temperature being 0 degrees Celsius and standard pressure being 1 atmosphere. So these are STP conditions. The last thing we learned was mole ratio, which is essentially a ratio. You can look at a chemical equation, and if you look at the coefficients within the chemical equation, that communicates the ratio of compounds within a chemical reaction. We call it a mole ratio because in chemistry we use moles. So essentially you can use any one of these conversions to basically answer any problem I would throw at you. The one thing I really want to highlight for you is, if you notice, all of them deal with moles. So if you can convert anything to moles, you can basically convert it to anything else beyond that. So now I'm going to run through some practice problems. Some of these are going to be ones that we've already done in class. Some of these are going to be new. So feel free to join in the video. You can also pause the video and try it yourself and then watch me explain it or look at the answer and see if you do it right as well. All right, here we go. If you produced 6.23 grams of zinc chloride, how many grams of zinc did you start off with? So these problems are always going to start off the same. I'm going to give you a value and I'm going to ask you to convert that value to something else. So our initial value here is 6.23 grams of zinc chloride. So I'm going to go ahead and start setting up my conversion by taking that initial value and putting it over 1. Then I'm going to convert that. So I'm going to put grams of zinc chloride on the bottom. And again, referring back to our toolbox, we know Avogadro's number, we know molar mass, we know molar volume, and we know mole ratio. Since this is dealing with grams, this is going to be molar mass. So what I can do is I can convert grams to moles. So I'm going to throw moles of zinc chloride on the top. I personally like to set up the entire problem first and then find values later, just to make sure I actually know what path I'm taking to get to where I want to go. So I've got moles of zinc chloride. Let's remind myself what I want. I would like grams of zinc. So I'm going to throw moles of zinc chloride on the bottom here in order to get rid of it. And now I need to figure out how I can get to grams of zinc. Since I already have moles of zinc chloride, what I'm going to actually do next is the mole ratio to convert moles of zinc chloride to moles of zinc. The ratio is kind of like your bridge between one compound to the next. Once you've got moles of zinc, you're basically almost there. You can convert moles of zinc to grams of zinc using the molar mass. So this is going to be my setup to get to where I want to go. All right. Next is filling in the values. For molar mass, we're going to get these values from the periodic table. And for mole ratio, we're going to get our values from the coefficients. So let's go ahead and do the molar masses first. So the molar mass of zinc chloride is going to be the molar mass of zinc. Work with me, please. Thank you. The molar mass of zinc, which is 65.37, plus the molar mass of 2 chlorines, which is 35.45. So let's go ahead and write these down. So 65.37, 35.45 multiplied by 2. If I go ahead and add these up together really quick, I'm going to get, and help if I knew how to type, 65.37. I'm going to get 136.27. Remember, this value is how many grams is equal to 1 mole. Because the idea is if you've got 1 mole of zinc chloride, you must have 1 mole of zinc and 2 moles of chlorine. So if you add up those values there. So I'm going to put this value, this 136.27 on the bottom, 1 mole on top. Mole ratio, we get these from the coefficients. So I'm going to go ahead and reference my chemical equation. I'm looking at zinc and zinc chloride. They both have a coefficient of 1 in front of them because this is just a 1-to-1 ratio. So 1-to-1. And then for the molar mass of zinc, I've already got that. We figured out it was 65.37. So 65.37 grams per 1 mole of zinc. So now I can go ahead and figure this out. So 6.23 divided by 136.27 times that by 65.37. Check your sig figs. Okay. Quarantine or no. 3 sig figs here. 5 here, 4 here. The rest of the values are exact. I don't need them. So you always go with the least number of sig figs. So 3. So my final answer is going to be 2.99 grams of zinc. So let's just take a moment and remind ourselves what we actually did. So my question was, if you produce 6.23 grams of zinc chloride, how many grams of zinc did you start off with? So I'm basically saying, hey, I made 6.23 grams of this. How many grams of that must I have needed in order to make that? That's what stoichiometry is allowing us to do. We're going to be able to do some more in-depth examples. We're going to do some labs kind of proving the math of this here as well, but this is kind of the concept behind it. All right, let's try another one. If you had 5 grams of hydrochloric acid, how many liters of hydrogen would you produce? All right, I've got my chemical equation. This is your starting value, so we're going to go ahead and take that value, so 5 grams of hydrochloric acid. I'm going to go ahead and throw that over 1. Set up your next step, throwing that on the bottom to cancel it out. So again, I've got grams, so this must be molar mass. So again, I can use molar mass to convert grams to moles. So I'm going to go to moles of hydrochloric acid. That's not what I'm looking for. I'm looking for liters of H2, so I can keep going. I can throw moles of hydrochloric acid on the bottom to cancel it out. So I've got moles of hydrochloric acid. I want liters of H2. So again, that ratio is kind of your bridge between compounds. So I can go from moles of hydrochloric acid to moles of H2. But I don't want moles of H2. So I can throw moles of H2 on the bottom, and then this is where you're going to use molar volume. Notice how this is asking for liters instead of grams. So we can do liters of H2 at the top. If this was being a better question, I would probably say at STP. So let's pretend it's at that. Okay. Let's go ahead and plug in our values. For molar mass, remember we're going to get those values from the periodic table. So for hydrochloric acid, it's going to be hydrogen and chlorine. So hydrogen is 1.01, chlorine is 35.45. Add them together. We're going to get 36.46 grams per 1 mole. Let's look at the ratio here, because remember that's where we're going to get the that from the coefficients. So it looks like it is a 2-to-1 ratio here. So 2 hydrochloric acids per 1 hydrogen. And then our molar volume value, if you remember, is 1 mole of any gas at STP is equivalent to 22.4 liters. Everything cancels out. We should be good to go to solve. So I'm going to go ahead and do my 5 grams of hydrochloric acid divided by 36.46. divide that also by 2, multiply that by 22.4 value, sig figs, I'm looking for 3, so it looks like I'm going to have 1.54 liters of H2. It's going to be my final answer. Again, so if I had 5 grams of hydrochloric acid, I could make 1.5 liters of hydrogen gas. All right, let's do one more example. If you recall this is actually from our very first lesson, but this is incorporating Avogadro's number, so I wanted to include it in this video here as well. So how many carbon dioxide molecules are in a sample with a mass of 36.5 grams? Okay, let's go. I gave you value. Take that value, put it over 1. Set up your work. So this is grams of carbon dioxide. Take that unit, throw it on the bottom. So I'm going to put grams of carbon dioxide on the bottom. This is going to be molar mass. If you've got grams, you can convert this to moles. So moles of carbon dioxide. And like I mentioned before, I like to set everything else first. So moles of carbon dioxide. Cool. Let's see what this is asking me again. So how many carbon dioxide molecules? So this is like if I could count like how many CO2s there are in a 36.5 gram sample. Now remember, atoms are ridiculously small. There's no way I could feasibly count this. I would be very dead before I got anywhere with it. But that's why we've got this concept of a mole. And if you recall, 1 mole is equal to 6.02 times 10 to the 23rd. So if I figure out how many moles of carbon dioxide I have, and if I know that 1 mole is equal to 6.02 times 10 to the 23rd of that individual molecule, then I know how many carbon dioxides I have. In order to figure out how many moles I have, I need to do the molar mass first. The molar mass of carbon is 12.01. Oxygen is 16, and there's 2 of them, so 16.00. I'm not doing that in my head. 32 plus 12.01 is going to be 44.01 grams in 1 mole. So I would encourage you to calculate this on your own if you've got your calculator with you, just because once you've got these large exponents, you're more prone to type in a mistake. So boom, sig figs, I'm looking for 3 because of my 36.5, that's my least. This has 4, and remember this is actually a measured value as well. This is actually a calculated number. So for my 3 sig figs, I'm getting 4.99 times 10 to the 23rd carbon dioxide molecules. I'm getting that E value in my calculator. Meow, 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 meow. Do you see? Remember that just stands for 10 to the for an exponent. Okay. So that's an example of using Avogadro's number. So now how many oxygen atoms are in the above sample? So this is 4.99 times 10 to the 23rd carbon dioxide. Now I want to know how many oxygens. So easy numbers really quick. If I had, let's say, 5 CO2s, how many O's do I have? Well, if I've got 5 CO2s, and there's 2 O's per CO2, and if I've got 5 of them, 5 times 2, I'd have 10, right? That's the idea up here. The numbers are just bigger and scarier. So basically, if there are 2 oxygens per every CO2, and this is how many CO2s I have, well, I'm just going to take this value and multiply it by 2. So 4.99 times 10 to the 23rd times 2. I am getting 9.99 times 10 to the 23rd oxygen atoms. Again, I'm looking for 3 sig figs. That multiplying by 2 is exact because there's exactly 2 oxygens per every carbon dioxide. Okay, here's a couple, those are a couple different examples utilizing everything that we've learned so far in our toolbox. I'm going to provide some additional practice resources for you during this time. Please do not hesitate to reach out to me, email me, we can Google Hang, we can Google Chat if you just need some extra practice with any of this stuff. Hope you're all doing well. Make sure you're staying healthy.